So in the last class, uh, we were discussing about different primitive data types in the C programming language. So primitive data types. So these primitive data types, at the end of the day, we have seen in the last class that everything has to be represented in the form of bits. Okay, so we try to understand this aspect of representation, data representation in today's lecture to some extent. So if you take int, so there are two kinds of integer. One is signed, other is unsigned. And then we know there are, we have a short int, we have default regular sized int, and then long int. And then we have floating point data type, double, long double. Number 3, we have char. Number 4 is underscore. So the representation of Boolean data type underneath is very simple. So it's there are many ways of doing it. It's and for characters, every alphabet has a encoding, has a decimal value or an ASCII code associated with it, and that ASCII code will be represented in a binary form. And when we come to float, double, and long double, when we come to, so that here things are pretty complex actually. So if we have some number like 3.146, this is the number that you have, and when it gets stored, it gets stored in the binary in some particular format. So there are what are called as IEEE 754 or 756 floating point representation, double representation formats for double data types of double, so on and so forth. So what happens is, this is the space in which we are comfortable with these decimal numbers, but computers can work in this space, that is in the space of binary digits. So this will be translated into a binary form in a particular format. And when we want data back, when we want to view or analyze this data, this binary representation will be mapped back to the decimal representation and will be shown to us on the screen. And when we do arithmetic operations on floating point numbers, all that arithmetic operation happens in this space. So arithmetic, all the computations, arithmetic, whatever that we do happens in this space. So because that arithmetic is being done by the computers, and all arithmetic will be done using circuits which act on binary numbers. So you work in this space, and when we want to view or analyze the data that is being generated, we map it back to decimal form and we try to view here. In this class, we will not spend time on this representation format, how floating point numbers are represented, and so how do we go back and forth. Those things we will not study, but this information is there in the textbook. So those of you who are interested, you can read them. But I would presume you will get an opportunity to learn about these ideas either in your digital systems and microcontrollers course or computer systems organization course. In one of these two courses, you may get an opportunity to learn about this mapping. But in today's lecture, we will focus to some extent on representation of integers, So if you look at integers, so So we are looking at signed and unsigned integers. Let's start with the unsigned integers. So if you have bits B31, so when we take a regular integer, default integer, which is of size 4 bytes or 32 bits, let's say the bits are B0 to B31. So there are 32 bits or 4 bytes. And so this is base 2. These are all each of these bits. No, they all belong to 0, 1. Either they are 0 or 1. And the value associated with this binary number is this sigma I is equal to 0 to 31 bi into 2 power I. This is the value associated with an unsigned integer. So if you take a simple example, let's say if you are working on 4-bit numbers, the value associated with this bit is 2 power 0, this bit is 2 power 1, this bit is 2 square, this bit is 2 cube. So what happens is the value that we get is 2 cube into, so the value that we get is 1 times 2 cube plus 0 times 2 square plus 0 times 2 power 1 plus 1 times 2 power 0. So you have 2 cube plus 0 plus 0 plus 1 or 2 power 0, which is equal to 9. So the value associated with this 1001 is 9. Okay. Are you with me here on this example? So if you are with me on this, can you tell me if we use regular integers, when we look at regular integers, what will be the smallest and what will be the largest value that you can represent? Or what will be the range of values that you can represent using a 32-bit integer, 32-bit unsigned integer? What is the smallest value that you can represent? Yeah, all bits are 0. So what is the largest value? Yeah. So the largest value when all the bits are equal to 0, when all the bits are equal to 0, you get 0. When all the bits are equal to 1, what you have is sigma I is equal to 0 to 31, 2 power I, and this is equal to 2 power 32 minus 1. So the range of values that you can represent using 32 bits is 0 to 2 power 32 minus 1. Great. So now let me write this here. The range of values that we can represent here is 0 to 2 power 32 minus 1. So this is for unsigned integers. So now let's look at signed integers. So in signed integers, there are different ways of representing numbers which are negative, where we have to represent negative numbers also. There are different ways. But the most popular one is what is called as a 2's complement representation. And that's what we will see now. So in 2's complement representation, so let's say you have bits B31 to B0 here, then so the way this works, the way the mapping works is this. The most significant bit will have a negative value. Okay. I is equal to 0 to 30 bi into 2 power. So this is the mapping function. So this is a, you may ask, no, how this function looks magical, but essentially what the important point here is the weight associated with B31 with the bit B31 is minus 2 power 31. So if you look at an example, so if you see 1001 and the value associated with this bit 1 is minus 2 square, and the value for this bit is 2 power, no, this is 2 cube. Two cube, 2 square, 2 power 1, 2 power 0. So what happens is the value is associated, the value of this number is minus okay, I'll make my life simple. I'll just write 1 times minus 2 cube. 1 times minus 2 cube plus 0 times 2 square plus 0 times 2 power 1 plus 1 times 2 power 0. So this is equal to minus 8 plus 0 plus 0 plus 1, which is equal to minus 7. So the same bit pattern 1001, when you think of it as a signed number, 2's complement signed number, its value is equal to minus 7. But when you think of it as an unsigned number, its value is equal to 9. Are you with me here? So the number 1001 by itself, it doesn't mean anything, but the semantics that we give to it is what makes that number. Okay. In general, if you look at a number, if bit B31, if it is equal to 1, this is what is called as a sign bit. If bit B31, if this is equal to 1, then what happens is the number is, if it's equal to 0, if it's equal to 0, then this whole value, no, this whole entity, it becomes equal to 0, then the number is a positive number. But if the bit B31, if it is equal to 1, then the number becomes a negative number. Why the number becomes a negative number? If it is equal to 1, the value that is coming out of this position is minus 2 power 31. And what is the max value that can come from this? What is the max value that can come from this? What is the max value that can come from the other? So the maximum value that can come from the other bits is 2 power 31 minus 1. So what happens is, even if you kind of have everything equal to 1 also, so what happens is when you add this with this, you still get minus 1. So when B31 is equal to 1, we know for sure it's a negative number. And if the bit B31 is equal to 0, then we know for sure it's a positive number. So if you want to know whether your number is positive or negative without using that greater than symbol, then you can use bitwise operators and check if the most significant bit is equal to 1 or not. And what is the range of numbers? What is the range of numbers you can represent using signed numbers in 2's complement form? What is the range? So the range is the most negative value will come. The most negative value will come when all these bits B0 to B30 are equal to 0 and B31 is equal to 1. And when B31 is equal to 1, so so when 1 followed by all zeros, you will have minus 2 power 31 plus the positive value contributed by all of them is equal to 0. So this is equal to minus 2. And when do you get the most positive value? When the sign bit is equal to 0 and everything else is equal to 1, in which case this is equal to 2 power 31 minus 1. So the range of values that you can represent, using this is minus 2 power 31 to 2 power 31 minus 1. Are you all with me here on the range computation? Are you all with me here? This one, how we got it? Geet has a question whether arithmetic operators are faster or bitwise operators are faster. Usually we can safely say bitwise operators are faster, Geet. Arithmetic operations, especially involving multiplication, they are expensive. But if there are equivalent bitwise operators, then they will definitely be much faster than arithmetic operations. So in today's, just to summarize what we have seen so far in today's lecture, the first thing that we have seen is like how these binary numbers are mapped to equivalent decimal numbers. And the second idea is, let me use a different color. This is the first idea. The second idea is the range. What is the range? The third idea is again, how the mapping function between signed numbers and the equivalent decimal numbers. Fourth idea is the range. And the fifth idea, which is important, is the same 100. If you consider it as a unsigned number, its value is equal to 9. But if you consider it as a signed number, its value is equal to -7. This is how, these are the important ideas that you have to keep in mind here. What we didn't see is how do we go from decimal to binary? We will see in the next class, or not next class actually. I will point you to a video, a small 15-minute video, which it's an interesting video. So I will talk about it at the end of the class. So now let's try to. Any questions so far? You're all doing good? Good, stdio.h. Okay, so this is, you are able to see the screen, right? The editor. How do we, I want to assign a number to, yeah, so let's say 4. Sorry guys, 1 minute. 1, 2, 3, 4, 5, 6, 7, 8. So what I am, so I'm just assigning to variable I uh, a binary number where all the bits are equal to 1. Where all the bits are equal to 1. We can achieve the same thing. We can achieve the same thing by saying I is equal to, since you read about bitwise operators in the last class, -1. So when you take 1 and left shift it to 31 or 32 bits actually. Yeah, not sure. Let's not get here. We may get into some trouble. Okay. Are you with me here? What is happening? So those of you who are wondering what is happening, I want you to make one point here. Let's say I is an unsigned integer. So you know it's an unsigned integer. So the range is 0 to 2 power 32 minus 1. So if you take any value in this range, we can assign it to, to an unsigned integer without any problem. And when we specify the unsigned integer specification, we can use different uh, base notations. Like for example, we can use a decimal notation, or you can use a binary notation, or you can use a hexadecimal notation. Today we will see what this hexadecimal notation is. Like for example, if you want to do in hexadecimal, it is much more easy. Everything will be converted into binary at the end of the day. Like for example, 0x, 0x stands for that the number is a hexadecimal number. So I can, this is a hexadecimal. So on line number 6, what you are doing an assignment in a hexadecimal form. But internally what happens is it gets stored as all ones, because what we are seeing on the screen on line number 6, that hexadecimal representation is equivalent to all ones. Or what is the binary value of 2 power 32 minus 1, not decimal value of 2 power 32 minus 1? What is the decimal value of 2 power 32 minus 1? Can you find out quickly? Huh. Agrim has it. Or if I just say this, all these three, line number 5, line number 6, line number 7 are the same, because internally at the end of the day, the computer stores the numbers in the binary form, right? So now, having said that, so we said, so printf, so unsigned I percent %u and signed I percent. So when we print it on the screen, what do you think gets printed when you run this code and print it and execute it? What do you think we will get? When we write code, so when we compile this code and execute the program, what gets printed on the screen? Yeah, you got it. So GCC overflow.c.a.out. Yeah, you can see. Yeah. You can see that I is equal to this and signed I is minus 1. So the all bits, no, when everything is equal to 1, so by itself it doesn't mean anything. But if you say %u, printf will interpret it as a unsigned integer and prints that value on the screen. And if you say %d, printf interprets it as a signed number and it gets a value of -1 and prints it on the screen. And actually, printf doesn't know anything. If you kind of say no, and maybe next line I will do it. So printf doesn't know. Let's see what gets printed. Can someone guess what gets printed? It's just a warning. Let's try to run it and see. it gave 0, but yeah, it can mean anything. Okay, so anyway, for the time being, just ignore this. Are you all with me here so far? Good. So now we will see some how we do arithmetic on binary numbers, and then we will come back and revisit some interesting things that can happen when we are writing programs. So in general, we would like to understand how arithmetic number representation for different bases will happen. So let's say if you have something like 843 to the base 10, what it means is 8 times 10 square plus 4 times 10 power 1 plus 3 times 10 power 0, right? And in general, if you have, so dk to d0 base b, then this value is equal to sigma I is equal to k dk into b power I. Sorry, not dk, di into b power I. All right. And yeah, so for example, and what is the necessary condition? That d naught to dk, they should belong to 0 to b minus 1. So for example, if we have something like 721 to the base 8, then its value is equal to 7 times 8 square plus 2 times 8 power 1 plus 1 times 8 power 0. What is its value? Can someone help me out here? 465. Thank you. So this is equal to 465 in base 10. And if we have, so is it, if you say 921 base 8, then this is wrong because 9 is not a valid digit in base 8. So when we are working with binary numbers, the base is equal to 2. So if you are working with binary numbers, bk2, yeah, so let me use the same notation. Base 2, then what we have is, this is what we get: sigma I is equal to 0 power k uh, d I into 2 power I, because the base is equal to 2 here, and this is the binary representation. All right. And then if you are working with hexadecimal numbers, in hexadecimal numbers, let me the base is 16. So if you are working with hexadecimal numbers, dx d naught to the base 16. So what we have is sigma I is equal to 0 power k di into 2 power, not 2 power, it is 16 power I. And then here, if you see this, the value, so the digits, these digits dk to d naught, they belong to the range 0 to 15. They belong to the range dk2, this is d naught. They belong to the range 0 to 615. And it is, so it's important to understand here. So if you see that the digits, if you look at hexadecimal digits, so 0 to 9, so not an issue. But then after that, 10 will be represented as A, and 11 as B, and 12 as C, 13 as D, 14 as E, and 15 as F. So if we have a number such as A1 in base 16, then this means this is equal to A times 16 power 1 plus 1 times 16 power 0. But the value of A is equal to 10, so it is 10 times 16 plus 1 times 16 power 0. So this is equal to 161 in base 10. Are you with me here? Does this make sense? So again, right now we are looking at how we are going from no, hexadecimal to decimal. But how do we move from the other way around? We will see in later. All right. So the next one important idea is the way binary and hexadecimal are related with each other, because this helps you in many places. Binary to hexadecimal and hexadecimal to binary. So let's see the relationship between binary to hexadecimal and vice versa. So let's say if we have B31 to B0 to the base 2, so we can, and we know this is equal to sigma I is equal to 0 to 31. Yeah, so Bi into 2 power I. This we know. We can rewrite this summation in this particular form. We can rewrite this as B3 into 2 cube plus B2 into 2 square plus B1 into 2 power 1 and B0 into 2 power 0. This is the first summation. And then we can write it as B7 into 2 cube plus B6 into 2 square plus B5 into 2 power 1 plus B4 into 2 power 6 into 2 power 4 we can write. Does this make sense? The second summation? Because when we take 2 power 4 inside, this 2 cube becomes 2 power 7, this 2 square becomes 2 power 6, this 2 power 1 becomes 2 power 5, and this is 2 power 0, sorry. This 2 power 0 becomes 2 power 4. Are you with me here? Are you with me in this, the way we are rewriting this summation? So similarly, we can do the same. So 2 cube and B10, 2 square, B9, 2 power 1, B8, 2 power 0, and this is equal to 2 power 8. So on and so forth. So I have a question for you here. What is the maximum value of the terms that are present in this summation? What is the maximum value of the terms present in this summation? Minimum. So if you look at the terms that are present here, so they all lie in the range 0 to 15, right? So what happens is, if you see this whole thing, this 2 power 4, we can rewrite it as 16, and this 2 power 8 is nothing but 16 square. So if you have a binary number, like for example 1001 and 0101, so what we can do is you split it into two parts. This part here, it corresponds to the first summation term here, and this part here, it corresponds to the second summation term here. And if you compute its value, it is 1, 2, 4, it is 6. And if you compute this value 1, 2, 4, 8, this is 9, okay, 96. So this whole binary number, it is equal to 96 to the base 16. So this whole number, which is to the base 2, it is equal to 96 to the base 16, where 9 and 6 are hexadecimal digits. So similarly, if we have, because this is equal to 9 times 16 plus 6 times 16 power 0. And this is exactly what we are doing here. So similarly, let's say if we consider one more number, 1100 and 0101, then what happens is, again, if you want to convert it into hexadecimal, it becomes easy. So this remains 6 and this remains, this becomes A. A or 1, 2, 4, 8. 8 plus 4 is 12. What is 12? 12 is 10 is A, 11 is B, 12 is C, C6 to the base 16. So its value, this value is equal to C times 16 power 1 plus 6 times 16 power 0. And this value and this value, they are exactly the same. So there is a lot of, and similarly, if someone tells you that a number, a hexadecimal number is 0xf0, and if you want to convert it to binary, all you have to do is you take this f and expand it to 4 ones, and you take this 0 and expand it to 4 zeros, and this whole thing is a binary form of this hexadecimal number. This particular thing has lots of advantages. This particular approach of moving between hexadecimal and binary, it has lots of advantages. Are you all with me here in this translation from binary to hexadecimal and hexadecimal to binary? So because of this, precisely because of this reason, for example, if you see the code that we have, I am not happy with with all these ones, counting this number of ones, whether we got the right number of ones is a pain, or you may have got the right number of ones, but while editing the program, while debugging, accidentally you pressed a backspace or deleted one, you really don't know that you lost a one there, and you get into trouble. But instead, if you take the equivalent hexadecimal representation, it is at least easy for you to know that there are 8 Fs here instead of 32 ones. Because if you take this hexadecimal one and convert it into binary, it's all ones, right? Does this make sense? Yes, no? But the conversion from decimal to binary is not that easy. So moving between this and this is very easy. Moving between hexadecimal to binary is easy, but moving from here to here manually is hard. It's a pain. Okay, but in terms of computer wise, it's all algorithmic, so it's all right. But for us, when we are writing programs and when we want to encode some logic, and if you would like to move between hexadecimal and binary, it's easy for us to work with it. All right. So now let's review some your primary school arithmetic. You may curse me for this, but still I want to kind of take a look at it and see what implications it has when we try to do the same. F means all ones. We studied, no? We just what in hexadecimal, the digits that we have are 0 to 9, 10, 11, 12, 13, 14, and 15. But when you want to write something like this is A, this is B, this is C, this is D, this is E, this is F. So if when we say a number is A1, hexadecimal number is A1, then that means the digit is this digit which we are calling it as A is nothing but 10. But similarly, if we say F1, the digit which we are calling it as F, it is nothing but 15. Does this make sense, Geet? Okay. So the high school or primary school arithmetic that all of us learned, so which we do in computers without blinking an eye, can cause some serious problems if you don't if you don't understand what happens underneath. So let's say we are adding two numbers, 432 plus 148. Okay. So what is 432? 432 is 4 hundreds and 3 tenths and 2 ones. Uh, yeah, 2 ones. This is not 0, this is ones. Okay, instead of, can you suggest me a different letter to use once, because we may get confused with the zeros? Okay, 2u. Okay, awesome. 2u's. And then, so 148 is 100 plus 4 tenths plus 8 units. Yeah, W. It's also good, good. So when we want to add these two numbers, we take 2 ones and 8 ones and we add, you get 10 ones. So what do we do? So we take this, so 8 ones and 2 ones is 110. We put this 110 up here and then we write 0 ones. So 4 tenths, 3 tenths and 110, this is 8 tenths. So we have 8 10 here. And then 400 and 100, you have 500. So, so finally we have 580. Good. You're all with me here? So now, um yeah, now let's take this problem slightly different. And let's say instead of 400, so 432, we have 648. If we have 648, so what we have is we have 600s, 4 tenths and 8 ones. And when we add 400 and no 6, yeah, so now so let's do. So when we have 400, when we add 400 with 600, what happens is we will get 10 hundreds and 10 hundred is 1000. So we say 1000 here, 1 th, 1000 comes here. And then there are 0 thousands here and there are 0 thousands here. So, and then you have 0 hundreds. So your 1000 comes here. But unfortunately, we don't have any space to store this digit. This 1000 digit, we don't have any space to store. So what happens is when we don't have any place to store, let's say, you know, what happens when someone tells you, when you're talking on mobile phone, when someone tells you the number, what happens? So you tend to forget some digits, right? So whatever, because you have limited memory and you try to remember, some digits gets overflown and you lose out. So similarly here, let's say if you have space only to store 3 digits, and if you generate one more digit, it gets discarded. So when you add 432 to 648, then what happens? You get 80. Are you with me here? Are you all with me? Yes, no? So you get into what is called as a overflow condition. So when you are doing arithmetic, this is not like your pen paper arithmetic where if you need an extra thing, paper, you kind of squeeze the digit out somewhere. Because when we are working in computers, the space that is allocated is limited. You cannot expand it on the fly. Are you all with me? Yes, no, Otherwa? You want me to wait? So now let's say, so now when we are working with binary numbers, so let's say we have a binary number 101101 and 0001. So this is equal to 1 times 2 square plus 1 times 2 power 1 plus 0 times, 1 times 2 cube, 1 times 2 power 1, 0 times 2 power 1 plus 1 times 2 power 0. So in other words, we have 1 8 and 1 4, and so in this number we have 1 8 and 1 4 and 0 2s and 1 2 power 0, that is 1 1 is present. And similarly here you have 0 8s, 0 4s and 0 2s, but we have 1 1. So when we try to do arithmetic here, what happens when we try to do arithmetic here? This is 1 2 power 0 and 1, when we add this you get 2. Okay, so you will have 1 2 power 1 here, we'll have 1 2 power 1 here, and we will have 0 2 power 0. Are you with me here? Why we will get that 1 2 power 1 up there? Because 1 plus 1 is 2, and that is 2 is nothing but 2 power 1. We keep it there. And when we add here, we will get 1 2 power 1 plus this. Similarly, here 1 2 square and 1 2 cube. So this is nothing but 1 1 1 0 this is in base 2. Does this binary arithmetic make sense? I hope you're all with me here. So now, let's change the story a bit. So now we want to add, one here, 1101 and 1001. And so what happens? So now it's the same story. So Geet asked for one more example, but Geet, just pay attention here. Yeah, since Geet asked for one more example, I just do the same within the same example. Okay. So 1011. So if it is 1011, the first thing you should check is the first number remains the same. So we have 1 8 and 1 4 and 0 2s and 1 1. 2 power 0 is 1. So here we have 1 8 and 0 4s and 1 2 and 1 1. Okay. So now when we add this one, let's try to redo this homework. Let's try to redo this and see what happens. So here this 2 power 0 is nothing but 1. This 2 power 0 is nothing but 1. So 1 plus 1 is 2. So you will write something like 1 2 power 1. But if it is a 2 power 1, it should go here. So we kind of carry this 2 power 1 up here and make this equal to 0. 0 2 power 0. And then you have 1 plus 1 2 power 1 and 1 2 power 1. We have 2 2 power 1s. When we add them, this is what we get, but this is nothing but 2 square. So we put this 1 2 square here, and we make this into 0 2 power 1s. And then we have 1 2 square and 1 2 square. When we add them together, we have 2 2 squares. But this 2 2 squares is nothing but 2 cube. So what should happen is, so we'll put 1 2 cube here, and this will become equal to 0. 0 2 square. Okay. So now we have three, we have 1 2 cube, and so here we have something like 3 2 cube. So what do? Is we divide this 3 2 cube into 3 2 cube is nothing but 2 2 cube into 3, 2 plus 1, that is 2 power 4 plus 2 cube. So what we do is we put 1 2 cube here, and then we will have 2 power, but what we have is we will have 1 2 power 4 coming up here. And now we get into a trouble because there is space for only 4 bits, but the answer generated a 5-bit answer. Because of that, we have to discard that 2 power 4. So again, we get into a overflow situation. Do you understand the overflow in this case? All of you? So this will have serious implications when we write programs. Okay, so when we write programs, this will have serious implications. So let's see. So this is the program which we have written in section B1. So let's say, so this is the story. The story is there is one guy. So let's end this story. So let's the story is how a greedy millionaire. Oh, my screen is not shared. Huh? Okay, just 1 minute, guys. So now we will conclude today's lecture with a story. Okay, so you don't get an opportunity to talk about stories, but today we will conclude with a nice story. So there is this guy who is super rich, and now he has tons of money in his bank account. Uh, so to the extent that his bank account is maxed out. On his way to the bank, no, he sees a $1 note on somewhere on the road, and no, he picks it up, and no, he says, "Yeah, let's get richer." And then he goes to the bank, and he deposits that $1 in the bank. So what happens to him after depositing that $1 in the bank? What happens to him? So he becomes a pauper. Okay, so he goes bankrupt. Huh. I didn't compile this code. Let me. So GCC overflow.c, control L. Oh, I'm still in here. Huh? Okay. So before going to bank, he is all high. He's all flaunting his riches. He gets greedy on the way for $1, and then he deposits in his account, and he becomes uh, bankrupt. But I will make this story. Let's make this story much more sad. Okay. So here the sad story here is this. Okay. So he's again he is very rich. Okay, he is super rich. And no, so he's all again flaunting his riches, and there is a programmer no who is happily using here all signed numbers because that's what he got used to. And again he got on the along the way he gets $1, he deposits $1. And what will happen now? So he just doesn't go bankrupt. He has a massive loan on his account just because he got greedy with it for $1. Okay. So that's the story of a sad millionaire. Durasa Dukkaniki Chetu. Yes, guys, this is a, yeah. Okay. Yeah, so that's it. So this is the story of a sad millionaire. We'll conclude it with this story today. You didn't get the second one, so I think it's very simple. So let's see. Uh, yeah, I'll just have a couple of minutes. So let's say we are working with, so that guy has $7, 1, 2, 4, $7, and then he added $1 to it. So this is $7. He added $1 to it. When he added $1, this becomes 1000, and the value of this is -8. So from $7 from being rich, $7 rich before, but now he becomes -$8. Okay, so that's all I have. What I want you to do is, there is one nice video I will post. It's 1.5 hour video, but I want you to watch only 15 minutes of that. All right, only 15 minutes you can watch. It's in one of the tutorial session, and we were just laid back and discussing, but 15 minutes of which 15 minutes is the place where we talk about conversion of numbers from one base to another base. And I use whiteboard there, so you can easily find out. And one of your classmates volunteered to point you to that the time on that video. Okay, so he will let you know. All right. So that's all I have. Happy Republic Day. See you next week. I will post 2 problems today, programming problems, because I couldn't yesterday.